This is Fabian Zanella, Senior Director of Research and Development at StemoniX. I'm here to talk to you about one of the posters that we were presenting this year at the Society of Toxicology meeting. This one is titled Simultaneous Assessment of Oncology Compound Efficacy and Toxicity in a Neuronal Human-Induced Pluripotent Stem Cell and Glioblastoma-based High-Throughput Screening Platform. In this work, we leverage our microbrain 3D platform that is comprised of neurospheroids, and we combine those with M-cherry tagged glioblastoma cells to be able to watch the invasive behavior of the malignant cells in the spheroids at the same time that we measure the activity of the neuronal network upon treatment with oncology compounds. So we start with the basic characterization of the model. As you can see here, our spheroids are comprised of a balanced population of cortical neurons and astrocytes. We can see here the astrocytes staining positive for GFAP and the neurons staining positive for MAP2. Those cells express the markers of functional neurons and astrocytes. So we see here the neurons expressing robust levels of synapsin 1 and the astrocytes expressing robust levels of aquaporin, indicating that the cells have the biochemical makeup to be able to be functional cells. And then we start doing a little bit of characterization of the platform here. One of the most attractive things about this platform is the reproducibility. So this is a 384 well plate in which you see the zoom in here. You see one spheroid per well. And if you look at the size distribution across the plate throughout different columns, you can see that it's quite reproducible. And we feel that that size homogeneity is key for us to be able to achieve homogeneous function as well, which is what we do here in the next figure. So if you see this heat map here, this is basal activity of the spheroids when we load them with a calcium sensitive dye. So you can see that the activity is very reproducible throughout the plate, linked probably with the robust reproducibility in the spheroid size. And if we zoom in into those wells, we will see that the calcium dye is oscillating over time. As you can see here across different wells, you have similar behavior, again highlighting reproducibility. And that also means that we have a high throughput measurable assay in which you can actually see disturbances in the network if you treat that with compounds that are hurting the neuron in some shape or form. Here we validate that the platform is responsive to classic neuromodulatory compounds. So you see things like canic acid. As you increase the concentration from low to high, we see an increase in activity up to the point that it becomes excitotoxic, and then you start seeing the activity going down again. We see, for example, 4-aminopyridine. As we increase the concentrations, we see that the activity of the network increases significantly. We also see a decrease in activity with CNQX, and also with TTX, tetrodotoxin as well. So having this functional platform at hand, we postulated that we could do the work that we propose in this poster, which is if we took glioblastoma cells, in this case we took the U87 glioblastoma line, we tagged them with the lentivirus carrying the M-cherry reporter, and if we added this tagged cells to the spheroids and then treated them with compounds, there would be four possible outcomes in a way. So you could watch how the cells would grow over time. So if you didn't treat the spheroids, you would see that the red cells would slowly start to take over until they reached a very high number in the spheroids. And if we treated them, that could be compounds that would be ineffective but safe. So you would see growth of the red cells over the spheroid, but as you would see in the calcium traces here at the bottom, there wouldn't be a drastic change in the activity of the network. You'd have compounds that could be ineffective but toxic. What that would mean is that you would see that the red cells would still be able to take over the spheroid, and at the same time you would see that there is damage to the oscillatory behavior of the calcium signal. You would have compounds that could be effective but toxic, and we believe that that will be the case for most chemotherapy. So you would see that there is an effect in the signaling, the calcium signaling in the cells, but at the same time we were able to hold back the red cells a little bit or eventually eliminate it. That will be very good. And finally, the compounds that could be effective and safe in that you'll be able to either hold back or remove the red cells and not have a measurable effect in the calcium signal. So with this at hand, we started to do a little bit more work and use that as a basis to guide our next experiments. The next one we did was to try to titrate the number of tag cells that we would add to the platform. So we looked at parameters like peak count and peak amplitude and saw how those shifted as we increased the number of cells, both at baseline with treatment with DMSO or treatment with 4-aminopyridine. And long story short, we determined that adding 200 of the tagged cells per well was ideal in the sense that it produced the least variability in the calcium signal while still being able to detect the presence of the red cells in there. What we did next was to take those 200 cells that we would add per spheroid and treat the plates with different compounds that are used in oncology. Some of them are actually therapies that are used in glioblastoma. So we use DMSO as our negative control. We use temozolomide, which is a standard of care for glioblastoma combined with radiotherapy, paclitaxel, carmustine, and cisplatin. So some of these compounds, as you may know, are quite toxic and don't cross the BBB, but they were used just as a proof of principle to be able to show that we could kill cells and induce toxicity. And we looked at different parameters here. So we used just a standard plate reader to measure red fluorescence to see if we could detect that and correlate that with the number of cells that was being added. This is the first part of the figure here. And you can see that as we increase the concentration of the drugs like cisplatin and carmustine are able to somewhat decrease the red fluorescent signal, interestingly, indicating that they're actually killing those cells. In parallel, we're doing cell viability with cell titer glow, so you can see very similar behavior between just a direct red fluorescence measurement and the cell titer glow, which cisplatin is shown as a compound that is killing most of the cells there. And then we looked at the functional parameters. So in the calcium assay, we looked at peak count and peak amplitude. And again, you see that cisplatin is definitely causing the most damage here, but you see that some of the other compounds also do show an impact in function at the highest concentrations tested. And this is true not only for peak count, but if we look at peak amplitude as well. So one of the interesting things about these calcium assays is that you can extract many different parameters from those peaks. So you can look at peak height, peak amplitude, peak count. I mean, in total, there are more than 27 parameters that you can look at. And here to try to take advantage of that, but at the same time, keep the story relatively simple, what we did was to plot in these radar plots peak count, peak amplitude, then data from the cell viability CTG assay, and the readings from the red fluorescence to try to create signatures of toxicity for those compounds as we increase their concentration. So again, interesting enough, you will see that the dotted line here is our DMSO, or negative control, and you can see how the diamond's shape gets distorted as we increase the concentrations of the compound, starting from the orange, the lowest dose, to blue, medium dose, and yellow, the highest dose. So for example, temozolomide and carmustine didn't show a very large or a significant distortion of those diamonds, which is potentially good in terms of toxicity. We may not be removing or preventing the growth of the red cells, but at the same time, we're not causing overt toxicity to the spheroids. On the flip side, if we look at the data from paclitaxel and cisplatin, you can see that those diamonds look severely affected. And this is not entirely surprising. Those drugs are known to be toxic, and especially cisplatin, the highest dose, you see that that diamond turns into something completely different dramatically there, indicating that those spheroids can actually be suffering. So to give a visual to that experiment, here are some representative images of the cells after treatment, before and after treatment, and matched with some of the calcium oscillation profiles that we got. So for example, cells treated with the MSO, this is 3 days after the red cells were seeded. You see that they're over here. And then post-treatment, which is 7 days after this experiment started, you see quite a bit of a presence of red cells in there. And when we look at paclitaxel, this is 10 micromolar. As the experiment starts, again, the red cells are there. At the end of the experiment, we do see that they may be a little bit of a holdback in their activity there. At the same time, we see that it did cause a little bit of toxicity, so you see that the oscillations are a little bit more flat than what we see here up the top. And finally, we have temozolomide, which again, together with radiotherapy, is the standard of care for glioblastoma. And we can see that unfortunately, it was not able at all to hold back the growth of the red cells, but at the same time, the calcium oscillation profile indicated that the compound is somewhat safe. So we are happy to discuss more with you. Please reach out to us if you have any questions about this work or anything else that we do at StemoniX.